Hi, I'm Lexi, and this is Squirrel. Today I'll be doing the end of term presentation for SE490. Quick reminder of what Squirrel is. It's a collaborative travel planning app. Groups can build a shared itinerary together, organize flights, hotel, and restaurants in one place, save place recommendations from friends, and share trip photos afterwards. The whole idea is to replace the scattered mess of group chat, screenshots, and spreadsheets people currently use to plan trips together. This is grounded in real user research. Out of the 44 survey responses, 85 of the survey participants travel in group, and 82% of them want to try an all-in-one travel app. Since 85% of the users travel in groups, concurrent edits are the norm and is not the edge case. And this is our base of our changes after mid-2. Now, I want to give a quick recap of where we're at mid-2. So by the point of mid-2, we got these things done. First of all, Google account and email password authentication. Second of all, a mobile version where we chose capacitor specifically so the UI stayed consistent between web and mobile instead of maintaining two separate code bases. Third, real-time itinerary sync. It was built on the push and subscribe model, so it scaled across multiple collaborators instead of everyone polling for results. And lastly, the friends recommendations feature. It allows batch user queries and parallel data loading to keep the feature fast. And after mid-2, we received some feedback. And the major feedback is to quantify the scalability goal. It's very easy to say the app scales. However, it's much harder to actually prove it. How do you measure a race condition? How do you quantify performance as the dataset grows? And this is how shaped this is how our feedback shapes this entire second half of the term. So I have identified some specific scalability risks in Squirrel. First of all, users can perform simultaneous actions like adding or editing activities, inviting collaborators, and delete or edit the same item at the same time. Second of all, there are some current latency issues as the number of activities in the trip grows. And third, there is some behavior under network loss and progress restoration. We don't want to let users lose all their data if they're disconnected from internet. As a result, we have came up with this approach of automated mock user test. So mock users make real Firestore calls against the Firebase emulator. It is an actual local Firebase instance. And then we run three categories of tests against it: concurrency, performance, and offline behavior. All of these run through the Vitis test runner, and then we generate the JSON result of the test, and then we generate an HTML report from there. This gives us more quantifiable numbers instead of guesses in terms of how scalable Squirrel is, and is also wired into CI/CD, so every MR gets retested automatically. This is what the very first test run looked like before any fix was applied. So out of the 15 total tests, 11 tests passed, and the pass rate is 73%. And there's some order collision issues and lost collaboration updates. So if user want to create trip details and activity concurrently, a lot of order collision will happen, and some people lose their status. And if the users add collaborators concurrently, there will be loss of updates and only a few of the actual collaborators are added. And as we can see from these performance tests, we measured how fetch latency scales on the left side here, and we measured how the subscription model work on the right side here. We can see if we go from 10 to 100 activities, the mean latency for fetch grow from 28 to 41 milliseconds, and this is acceptable. But from 100 to 500 activities, it jumped a lot to 113 milliseconds in the fetch mean here. And then there's a near linear increase when it comes to 1,000 activities. And the subscriptions stay fast as every size as we tested, so this is not a bottleneck. So from the performance test results, we know that the current implementation and fetch strategy only work well up to around 100 activities. And the real-time sync is not the bottleneck, but the code fetch is. So after running the first test with the mock user test, we have applied a couple fixes. So the first fix is about the collaborator data loss bug. Fix 1 addressed the collaborator data loss issue. This bug is basically a read modify write race. So both users are trying to read the collaborator array as owner, and both try to append their own ID locally. And whoever writes the full array last would win. And the other person's invite will be erased. And there's no error handling and no retry. So the first option we consider in terms of fixes is the Firestore transaction. It auto retries on conflicts and it sounds very right, but the transaction still need a read round trip on every single invite. And the retry logic also lacks latency under contention, and it is an overkill for this simple problem. So the approach we took instead was the array union approach. And this is just a server-side atomic write option. It means add this element if it's not already present. So there's no read needed at all, and it's just a single write. So with two concurrent array union A and array union B calls, both of the changes from users get merged to the array. And the second fix we have applied is for the activity order collision, and it was detected by our mock user test. So the bug is basically a read then write order assignment, reading the current activity count for the day, and then setting the new activities order equal to the count then write. If two people do this at the same time, they both read count 0 and both write order 0, and it will be a collision. Our first attempt of the fix was a create a tiebreaker, option A. And if two activities have the same order, we sort by the creation timestamp. And it is purely a client-side change, but it didn't really fix the bug because the duplicate order values are still being written to the database, and it masks a symptom instead of fixing it. And we also considered a single global atomic counter as option B here. However, it doesn't really distinguish between days, and per day orders would break down. So eventually we took option C here, a per day counter via transaction. So every create run inside a Firestore transaction, and it reads the counter for the day, assign a value to the order, and then atomically write the activities and increment the counter in the same commit. If two creates race, the second person's transaction retries automatically and picks up the updated counter. So it gets to the next unique slot. And after applying this fix, there is zero collision under the concurrent write. And we also identified a bug about create activities. So there is a data efficiency issue since create activity never actually wrote a status field. So every activity in Firestore has no status at all. And our fetch functions were just pulling the entire collection, and it includes all the activities and is really not efficient. And we're doing the filter from the client side. We tried the obvious fix first by just adding a server-side filter, like where status not equal to pending, but it actually breaks things because Firestore's inequality operators execute and exclude documents where the field doesn't exist at all. And since none of the activities have a status field, and they're all just vanished from the UI. We also tried migrating all the data and try to assign a status field before filtering, but the partial migration failure on production data is a risk we don't want to consider. So as a result, we took option C and we write status as confirmed as a source going forward, adding a server-side filter that catches new pending imports before they ever reach the client, and keep the client-side filter as a fallback for legacy documents. So there's no data loss, no migration risk, and new fetches only transfer confirmed activities. The last fix I have applied is about the science failure on delete and edit race. If user A deleted activities right before user B save and edit to the same activity, the edit can return success, and B will think the change is saved, but there's nothing there as this activity was already deleted. And I consider wrapping every update in a transaction that check the document exists first, but it adds an extra reads to every single save. Since this silent failure is one of the rare scenario, it's not really optimal to add an extra latency for the happy case. So instead, I have took this option B of the catch not found error. We let the write happen optimistically, and there's zero overhead in the normal case. If Firestore comes back with a not found error, we would catch it and throw a clear message. And the Firestore's real-time listener self-correct the UI regardless. So on the user side, there's not much error that's being displayed. So after these fixes, I reran the mock user test and we passed all the tests with no order collisions and no lost collaborators. And these are the comparison before the fix and after the fix. Beside running the mock user test, I have also implemented the mock user test in the CI/CD pipeline. So now in GitLab, after some commit and before every merge request is actually being merged, we run through these mock user tests first and make sure all the changes are still adaptable with our scalability goals. After making changes for this summer SE490 team, I have updated some plans and to-dos for the fall SE490 team. So first of all, we want to continue with the mock user test, and we want to expand on the existing test suite by adding more offline tests and more areas in terms of scalability and usability of the project. And second, we want to build the features missing currently in the Squiro project, such as invite and registered users, and building the trip memory section, as well as the mobile version launch on App Store and in production. And there's some more features to go. And third of all, we need some more performance improvements as from the performance test currently, there's a bottleneck on the fetch currency latency, and the performance is steady for around 100 activities, but we definitely need to optimize for more activities and for more users as our user base expand. And the last plan will be making more quantifiable user experience goal to make sure our app is user friendly and make sure the user experience goes well. My plan would be performing user task observation with a time target and silently observe when the user trying to perform action and set a time goal for it. So some of the smaller tasks or major tasks would be complete login flow, and the target would be around 2 minutes. And some other tasks would be making sure the user can create a trip and invite collaborator within 2 minutes and add an activity within 30 seconds. And from the mobile versus the desktop version, there should be minimal slowdown when it comes to using the mobile version. and the core task success rate should be more than 80% when the users don't get any instruction from the team.